This is the genus Iris. These plants are found across the temperate regions of the Northern Hemisphere, thriving in environments that range from dry, rocky mountainsides to wet marshes and riverbanks. One of the most recognizable features of an iris flower is its structure, especially the drooping lower petals, known as the falls, which often carry a distinctive beard or crest. Beyond their beauty, irises play important roles in their ecosystems. They attract a wide variety of pollinators and, in wet environments, even contribute to water purification. But here's the challenge. The genus Iris contains roughly 300 different species, each adapted to a unique ecological niche. Because of this diversity, successful cultivation depends heavily on matching the right species to the right environmental conditions. What works perfectly for one iris species could be disastrous for another. An experienced botanist can usually identify an iris species just by examining its physical characteristics and, from that, infer the environmental conditions it prefers. The problem is that many regions around the world don't have easy access to highly skilled botanists who can reliably make these identifications. This lack of expertise makes large-scale or accurate iris cultivation much more difficult. So how do we solve this? The idea is simple but powerful. We ask a botanist, or a group of botanists, to label a large number of recorded iris flowers, meaning they identify the species of each flower. We then use these labeled examples to train a computer program using machine learning. The goal of the learning algorithm is to automatically adjust itself so that its predictions match the botanist's labels as closely as possible. If the training succeeds, the program should then be able to predict the species of completely new iris flowers it has never seen before. This approach is known as supervised learning. To demonstrate this, we'll use the famous Iris Dataset introduced by Ronald A. Fisher in his 1936 paper, The Use of Multiple Measurements in Taxonomic Problems. You can find a link to the paper in the description. This dataset contains measurements of the sepal length, sepal width, petal length, and petal width for 150 iris flowers. These flowers belong to 3 species: Setosa, Versicolor, and Virginica. Our goal is to train a machine learning model that can predict the species of an iris flower based on these measurements. To follow along, you'll need Anaconda and Visual Studio Code installed. Links to both are in the description below. Once you've installed them, open Visual Studio Code and navigate to your working folder. Create a new interactive Python notebook, making sure the file extension is .ipynb, which stands for Interactive Python Notebook. If this is your first time doing this, Visual Studio Code will prompt you to install some extensions, including the Python and Jupyter extensions. Go ahead and install them. Then click the Select Kernel button, choose Python Environments, and select the Conda environment. If Anaconda is installed correctly, it should appear in the list. Click the plus button to insert a new cell. This cell will be used to run your code. To test that everything is working, type the classic Hello World line and run the cell. You can do this by clicking the play button next to the cell, or by using the keyboard shortcut Shift plus Enter. If you see the output appear below the cell, your setup is good to go. Now it's time to encounter our first real machine learning algorithm. We'll start with a relatively simple but powerful method called K-nearest neighbors, or KNN. Most supervised machine learning methods are built on a simple intuition. If a test data point is close to a training data point, then its predicted output should be similar to the output of that training point. KNN turns this idea directly into an algorithm. Imagine plotting the sepal length and sepal width of iris flowers belonging to 2 different species, which we'll call Class A and Class B. Now suppose we plot a new iris flower whose species we don't know. How do we predict its species? First, we compute the Euclidean distance between this unknown point and every point in the training data. Then we find the training point with the shortest distance and assign its species to the unknown flower. This simplest version is called the one nearest neighbor method. While it's easy to understand, it's often too simplistic for real-world problems. To improve it, we extend the idea to consider not just one neighbour, but the k nearest neighbours. For example, if we choose k equal to 5, we look at the 5 closest training points. The species that appears most frequently among those 5 neighbours becomes the prediction. If 3 of the 5 closest points belong to Class A, then we predict that the unknown iris also belongs to Class A. Now that we understand the idea behind KNN, let's load the dataset into Visual Studio Code. Make sure the dataset file is in your working folder. We start by importing the pandas library, which is a Python library used for data manipulation and analysis. By convention, pandas is imported as PD. Pandas can read many different file formats. Since our dataset is stored as a CSV file, we use the read-csv function. Visual Studio Code helps here by offering code completion suggestions as you type. Once we run the code, we see a preview of the dataset. There are 150 samples and 5 columns. The first 4 columns contain measurements of sepal length, sepal width, petal length, and petal width, and the final column contains the species label. We store this dataset in a variable, so we can reference it throughout the code. Next, we inspect the data for missing values and incorrect data types. We do this by calling the info method on the dataset. The output shows that all columns contain 150 non-null values, meaning there are no missing entries. The first 4 columns are stored as floating point numbers, which is exactly what we want, and the species column is stored as an object type, which is appropriate for categorical data. We then check how many samples belong to each species. To do this, we access the species column and apply the value counts method. The result shows that there are exactly 50 samples for each species, which means the dataset is perfectly balanced. Now let's visualize the data. We import pyplot from matplotlib and Seaborn, which is built on top of matplotlib and makes statistical visualization much easier. By convention, pyplot is imported as pli, lt, and Seaborn as SNS. Using Seaborn, we create a pair plot of the dataset and color the points based on species. Then, we use pyplot to display the plot cleanly. This produces plots of every feature against every other feature. Along the diagonal, where each feature is plotted against itself, we see distribution plots for each species. The distributions are mostly normal, and one thing stands out immediately. The Setosa species is clearly separated from the others, with very little overlap. We also generate box plots for the 4 features. These show the range of values in each feature. Petal length has the largest range, while sepal width has the smallest. Next, we prepare the data for modelling. We store the 4 measurement features in a variable called x, which represents the input variables. The species column is stored in a variable called y, which represents the output variable. To estimate how well our model will perform on new, unseen data, we set aside a portion of the dataset as holdout validation data, often called test data. This data is not used during training and is only used to evaluate the model's performance. While this means we train on less data, it gives us a more realistic estimate of how the model will behave in production. We do this using the train-test-split function from scikit-learn, which is a free and open-source Python machine learning library. We pass in x and y, and we specify that 30% of the data should be held out for testing, leaving 70% for training. Because the split is random, we set a random state so our results are reproducible. We also stratify the split by species to ensure that each species is represented equally in both the training and test sets. After running this, we end up with 4 datasets: xtrain and ytrain for training, and xtest and ytest for testing. The training set contains 105 samples, and the test set contains the remaining 45. Now we import the k-neighbours classifier from scikit-learn. This model requires the number of neighbours as an input parameter. For now, we set k to 5. We also specify the type of weighting. By default, the weights are uniform, meaning all neighbours contribute equally to the prediction. If we use distance weighting, closer neighbours have more influence. We store the model in a variable and train it using the fit method on the training data. Once trained, we use the model to predict the species of the samples in the xtest dataset. To evaluate the predictions, we compare them to the actual species stored in y-test using a confusion matrix. If the predictions were perfect, we would see only values along the diagonal with zeros everywhere else. In our case, we see that the model performs extremely well with just a single misclassification. The order of species in the confusion matrix corresponds to the order learned during training. We can confirm this using the classes attribute of the model. The first diagonal entry corresponds to Cetacer, the second to Versicolor, and the third to Virginica. The single error occurs where a Virginica sample is misclassified as Versicolor. From the confusion matrix, we compute the model's accuracy using the accuracy score function from scikit-learn. An accuracy of 1, or 100%, would mean no misclassifications. Our model achieves an accuracy of 98%, meaning it is only wrong about 2% of the time when predicting iris species in production. To make this concrete, suppose we have an iris flower with a sepal length of 5.1 centimeters, a sepal width of 3.5 centimeters, a petal length of 1.4 centimeters, and a petal width of 0.2 centimeters. When we feed these measurements into the trained model, it predicts that the flower belongs to the Setosa species with 98% certainty. If you're enjoying the video so far, don't forget to subscribe and turn on notifications so you don't miss future uploads. You might be wondering whether holding out more data would give us a better estimate of the model's error. In general, the more validation data we have, the more confident we are in our performance estimate. But there's a trade-off. Holding out more data means less data is available for training. When data sets are large, this isn't a big issue. But when data is limited, it becomes a serious problem. This is where k-fold cross-validation comes in. The idea is to repeat the holdout validation process multiple times, each time using a different portion of the data as the validation set. In 5-fold cross-validation, for example, the model is trained and evaluated 5 times, each with a different validation split. We use the stratified k-fold variant, which ensures that each fold maintains the same proportion of species. We also import cross-val score to compute the accuracy for each fold. We set the number of folds to 5, enable shuffling, and fix the random state for reproducibility. Running cross-validation gives us 5 accuracy scores. Taking the average of these scores gives us a more reliable estimate of the model's performance. In this case, the average accuracy is about 97%. Another important question is how to choose the value of k, the number of neighbors. Since k is not learned automatically by the model, but chosen by the user, it is called a hyperparameter. Earlier, we used k equal to 5, but what if k equal to 10 works better? And what about using distance-based weighting instead of uniform weighting? To answer these questions, we use grid search cross-validation. Grid search systematically explores a predefined range of hyperparameter values to find the combination that produces the best performance. We import grid search CV from scikit-learn and define a hyperparameter grid. For the number of neighbors, we test odd values from 1 to 21. For the weights, we test both uniform and distance-based options. We then run grid search using 5-fold cross-validation and accuracy as the scoring metric. This means the model is trained and evaluated 110 times in total. After the search completes, the best hyperparameters turn out to be 15 neighbors with uniform weighting, achieving an accuracy of 98%. With these optimized settings, the model again predicts that our example iris flower belongs to the Setosa species with 98% certainty. And that's how scientists use machine learning to predict the species of iris flowers. But the story doesn't end here. K-nearest neighbors is just one supervised learning method. In the next section, we'll explore decision tree models and see whether we can push the accuracy even higher. Thanks for watching. If you enjoyed the video, give it a like and subscribe. I'll see you in the next one. Bye!